So today's speaker is Shah from University of Notre Dame, and you can see his title right there up on the screen. So take it away, Jay.
Thanks for the invitation, Dan. It's a pleasure to speak. So in this talk, by C2 spectra, I'll mean what people usually call genuine C2 spectra, i.e., I have a sequence of pointed C2 spaces, x0, x1, x2, and so on and so forth, such that xn is the row-fold loop space on xn plus 1, where rho is the C2 regular representation. This actually defines the infinity category of C2 spectra for me by this sort of prescription of the objects. So I'll let that denote the inverse limit along the row-fold loop functors of, well, taking this inverse limit where SBC C2 plus denotes pointed C2 spaces. But I want to begin by discussing a calculation. It's an illustration of the general method that I want to describe today. So I'll let F2 underline be the constant C2 Mackey functor at the abelian group F2. And in terms of a C2 spectrum, let's let HF2 be the Eilenberg-MacLane C2 spectrum. And let's let SKL be SK minus L smash SL sigma, where sigma is the C2 sign representation. And this yields a definition of the C2 equivariant homotopy groups, pi C2K comma L of a C2 spectrum E, that's homotopy classes of maps SK comma L into E taken in C2 spectra. These are actually the ROC2 graded homotopy groups. And the problem I want to first consider is the following. So I want to compute the C2 equivariant homotopy groups of HF2. In other words, compute the ROC2 graded homology of a point with these F2 underlying coefficients. And there are multiple ways to accomplish this calculation, but in doing this calculation, I want to illustrate the method. So I want to exploit the connection between C2 equivariant and real motivic homotopy theory. So how does motivic homotopy theory enter the game? Well, the basic idea behind this is that if I have a real variety, then I can take its complex points, and this is actually a topological space because I can endow the set of complex points with the complex analytic topology. Moreover, since it's a real variety, I have an action by C2 via complex conjugation. And if you think for a second, you'll see that if I take the C2 invariance by this action, that's actually homeomorphic to the real points of R, given the real analytic topology, for example. Well, to get from topological spaces to the homotopy theory of C2 spaces, in terms of C2 spaces, what I mean is Parecis on the orbit category following Elmendorf, I suppose. So the orbit category OC2 is C2 mod 1. That's the cardinality 2 orbit with the C2 action mapping to C2 mod C2. And I get as a C2 space in that sense, XR to X of C with the C2 action. Since it's a pre-sheaf, I flip the arrows. Well, by this C2 space, I'll actually just note this by X of C, leaving the C2 fixed points implicit. So this assignment of C2 space to a real variety extends to define the functor of C2 Betti realization. That's a functor BEC2 going from real motivic spectra, which I'll denote by SH of R, to that category of C2 spectra from that I defined. And this is arranged so that I send a suspension spectrum of a real variety to its C2 space of points, where I've taken, of course, the suspension spectrum again. So this is a colimit preserving functor, and it admits a right adjoint. And if I need to refer to this, I'll call this right adjoint Sing C2. So why is this functor relevant for calculating the C2 equivariant homotopy of the Eilenberg-MacLane spectrum? Well, you have a result of Heller and Ormsby, which explains the relevance. So if HA sub R is the motivic cohomology spectrum over R with A coefficients, then the C2 Betti realization of HAR, that's actually equivalent to HA underline, where that's the constant C2 Mackey functor at A. In particular, of course, if I take HF2 sub R, that's equivalent to HF2 underline. Now, let's couple that with a result of Voevodsky. So let me let SKL be SK minus L smash GM smash L, generically denote the bigraded motivic spheres in SH of a scheme. So pi R star star of HF2 makes sense. I'm looking at the bigraded motivic homotopy groups, that real motivic cohomology spectrum, mod 2 coefficients. Voevodsky calculated this guy to be F2 adjoint 2 elements, rho and tau. And this is a bigraded polynomial ring. Grading is like this. So tau lives in degree 0, -1, and rho lives in degree -1, -1. And now let me rephrase the problem from before that you were thinking about. So I want to leverage Voevodsky's computation of the R motivic homotopy groups of HF2.
Excuse me, this
Yes,
is
go
Doug
ahead.
Ravenel. Hello. I want to ask a question. You're using the symbol rho to mean two different things here. I'm just warning the rest of the audience about that. Rho earlier used rho to stand for the regular representation, right?
Oh yes, of course.
Now you're
That's
using
right.
it to denote a certain element in motivic homotopy.
Right, and also, like, I forget, there's, like, Doug will know this, like, tau and rho correspond to, like, elements A and U that are often used. I forget which one is which.
I forget which one is which, too, but...
Okay.
Yes, so I will actually get to that later in the talk when I discuss the connection between real motivic and XC2 equivariant. So the tau and rho elements in the motivic situation, tau corresponds to U and rho corresponds to A. And A is the Euler class of the sign representation. But we'll get to that. Does that answer the question?
Yeah. Yeah.
Okay, so that let me make a note of that. So rho is different, is a different rho. And I'll never use the regular representation rho again. C2 regular at the row. That's a good point. Okay, so to continue, I want to leverage the calculation of Voevodsky to compute pi C2 star star of H F2 underline. And at the very least, let's note that I have a map. So since the C2 Betti realization of the bigraded motivic sphere is the same C2 equivariant sphere with the same grading, I have a map of homotopy groups from real motivic to C2 equivariant. Now, to effectively use the real motivic calculation to deduce the C2 equivariant calculation, I have to introduce a separate technique. So let me now discuss the separate technique of the Tate fracture flip, which is, I think, originally considered by Greenlees and May. So let's let EC2 be the free, contractible C2 space and form the cofiber sequence EC2 plus to S0 to EC2 twiddle. You can form this in pointed C2 spaces, but let me suppress suspension spectra symbols and just form this in C2 spectra. Because S0 to EC2 twiddle is an idempotent object. That is to say, if I smash EC2 twiddle with itself, I get it back. That's with respect to smash product. Well, in such a situation, I always get a fracture square of the following form. So this is the so-called Tate fracture square. I have X in the upper left-hand corner, which I want to decompose. That's a C2 spectrum. I can smash it with EC2 twiddle, or I can HOM in EC2 plus using the internal HOM in C2 spectra. And in the lower right-hand corner, I can combine these two operations, HOMing in EC2 plus first, and then smash with EC2 twiddle. And this is a homotopy pullback square of C2 spectra. Let me denote these symbols by a more concise notation. So I'll denote X smash EC2 twiddle by X upper phi. HOMing in EC2 plus into X will be denoted by X upper H, and the remaining guy will be denoted by X upper T. If you haven't considered this sort of pullback square of C2 spectra before, you've probably thought about a pullback square of spectra that I can obtain from this by taking C2 categorical fixed points, which is likely more familiar. If I take C2 categorical fixed points, that's this functor C2 from C2 spectra to spectra, I get a description of the C2 categorical fixed points of X in terms of the geometric C2 fixed points, the homotopy C2 fixed points, and the C2 Tate construction. Again, that's a pullback spectrum, homotopy pullback. Now, I want to consider, however, the pullback square of C2 spectra. And you also might be familiar with a different pullback square, which I'll describe shortly, but let me just say that the Tate fracture square agrees with the A arithmetic square where A is the Euler class for the sign representation, sigma. I write A as going from S minus sigma to S0. This is dual to maybe what people usually write as the Euler class, going from S0 to S sigma. So this is dual to that. The A arithmetic square is what happens if I combine the operations of A, inverting class A and completing with respect to A. Oh, sorry. So I can invert A on a C2 spectrum X. I can perform that operation at the level of spectra. I can also complete with respect to A. And I can complete and then invert. So think about, for instance, the arithmetic square with respect to P completion and P inversion is analogous to this. And this is the same as the Tate fracture square, where the identification uses the following fact. So I use that I have a cofounder sequence, C2 plus, going to S0, going to S sigma, which moreover dualizes to S minus sigma to S0 to C2 plus, where I've used that the C2 orbits and C2 spectra are self-dual. So that's a maybe recollection of something that is very familiar to the people in this audience. But this sort of technique works for any C2 spectrum X. However, if X happens to be the C2 Betti realization of a real motivic spectrum Z, I can attempt to take this A arithmetic square and match it with the so-called rho arithmetic square, which is something that I have in motivic homotopy theory. This rho is going to be the same element rho that appeared in the motivic homology of a point above. Well, the element rho is an element from S minus 1 minus 1 to S0, 0, which is dual to S0 to GM. That works in any motivic, stable motivic infinity category, SH attached to a scheme, and it corresponds to minus 1 in the ring of functions of S. Well, in SHR, if I take the C2 Betti realization of that element rho, it's clear that I'm just getting the Euler class A. So the element rho matches up with the element A. The question is then well posed. You can envision the rho arithmetic square formed in real motivic spectra as relating to the A arithmetic square, and thereby furnishing a method of calculation. Well, to implement the idea of relating the rho arithmetic square with the A arithmetic square, I can work on the pieces of that fracture square individually or independently. So let's do that. The first thing I can tackle is the so-called geometric part. So the geometric localization, that's just thinking about that upper right-hand corner, upper here, I've circled it, X upper phi. Well, I told you that C2 Betti realization, there's colimits, it's left adjoint. And it sends rho to A, so it sends HF2 rho inverse to HF2 A inverse. That furnishes a map from the bigraded real motivic homotopy of HF2 rho inverse to the C2 equivariant homotopy of HF2A inverse. The bigraded homotopy on the left-hand side, that's easily calculated. I'm just inverting rho at the level of homotopy groups. So that's just F2 adjoint tau rho plus or minus 1. And you might hope that this here is an isomorphism, this comparison map. And as I'll explain later on, that hope is correct. And this is essentially a result of Bachmann. Well, a very special case of a result of Tom. So that deals with the geometric localization. The more subtle part is how to deal with the homotopy completion. So the homotopy, by homotopy completion, I mean the X sub H part. So if you think about X going to X upper H as an endofunctor of C2 spectra, in fact, this is a localization. And it corresponds to the following adjunction. So I have C2 spectra, and I have Borel C2 spectra, which is infinity category equivalent to the category of functors from BC2 to spectra. So I'm just looking at spectra with external C2 action. By BC2, I mean the groupoid, where I have a single object and a C2 worth of endomorphisms of that object. Now, let me denote this adjunction by J upper star and J lower star. So, as I said, this is a localization, so J lower star is fully faithful. Let's depict this vertically. So I have C2 spectra, J upper star, Borel C2 spectra, and now I can forget the action to get the spectra, and this composite turns out to be the restriction functor. On the other hand, in motivic homotopy theory, I have the functor from SHR to C2 spectra given by C2 Betti realization. I also have the functor from complex motivic spectra to spectra given by complex Betti realization formed in the same way. And I also have the analog restriction motivically, which is base change. So if I have spec C, and I denote the structure map as C to spec R, which corresponds to R going to C, then I have C upper star, and that commutes with restriction. So this commutes. So if I want to understand the homotopy completion, the upshot of this discussion is that I better understand what's going on at the level of complex Betti realization. So as a first step, understand the complex story. Luckily for us, Duggar and Isaacson have a complete understanding of this, essentially. So they proved the following. Let X be a cellular complex motivic spectrum. Cellular means that I'm a spectrum generated as a in the localizing subcategory generated by the bigraded motivic spheres. Then after two completion, I have a so-called tau self map on X. And by tau self map, well, one way to say that is if you apply the Hurewicz homomorphism, it realizes the element tau for F2 homology. Tau is that element in the motivic homotopy groups of HF2, the complex category. If I look at this tau self map, then if I take pi c kl and I invert tau on X, that is isomorphic to pi k of the complex Betti realization of X. Again, 2 completed. So I can compute the homotopic groups of the complex Betti realization in terms of inverting tau on X, or inverting tau on the bigraded complex motivic homotopic groups. So I can, in other words, compute the restriction of C2 Betti realization in this manner. Now, I want to bootstrap to the C2 Borel spectra. That's like going from cofiber of A to A complete. So here's a plausible guess as to how to accomplish this lift of this result of Duggar and Isaacson. Let's guess that for cellular real motivic spectrum X, after 2 completion, I can invert some element tau on the row completion of X, thereby obtaining an isomorphism. If I row complete and then have this tau inversion, that's isomorphic to C2 equivariant homotopy of the C2 Betti realization of X after I take the homotopy completion. In particular, returning to our example, we'll see that this homotopy completion for HF2, its bigraded C2 equivariant homotopy is isomorphic to just inverting tau in terms of the real motivic homotopy of HF2. Note that there's the thing is already row complete because I'm thinking about that completion in the graded sense. So row completion step is already done for you, and I just have to invert that element tau. Okay, so there's one more thing that remains to be done. So finally, I have to deal with that Tate part, the lower right-hand corner of the Tate fracture square. So I get for that it's isomorphic to taking the HF2 upper H and then inverting rho, which is just F2 adjoin tau plus or minus 1 and rho plus or minus 1. So I just have both tau and rho inverted now. Taking these three calculations, we can combine them using the Tate fracture square. Again, let me repeat myself. I have HF2 phi, HF2H, HF2T, and I can use the Meyer-Vittoris sequence to calculate to calculate the C2 equivariant homotopy of HF2. Let me write that calculation down for you. So if you run through this argument, you'll get the bigraded groups to be F2 adjoin tau rho. That's the motivic part. Plus the so-called negative cone. So let me write it this way. I have F2 tau rho, tau infinity, rho infinity, on the class boundary of tau inverse, rho inverse. Boundary comes from the Meyer-Vittoris sequence. The grading is such that that class is in by degree 0, 2. And this is infinitely divisible by tau and rho. That's what that notation means. If this seems a bit opaque, let me now display a graphic which should make it pretty obvious as to how you combine these calculations to get this other calculation. So here I've displayed the calculation. Oops. So you can observe that in the gray shaded region, I have the motivic cohomology of a point, that the motivic contribution, and then I have this negative cone which appears because I've done this procedure of inverting rho, inverting tau, and then combining these two pieces. If you work it out, then you'll see that this picture is the right picture, which describes the C2 equivariant homotopy of HF2. Okay. Now, this calculation here is an instance of a general paradigm. Let me now state the main theorem of our work of Barron's. So let's let SH cell of R be the infinity category of cellular real motivic spectra. Then after 2 completion, the adjunction between SH cell R and C2 spectra, where the left adjoint is C2 Bethe realization, the right adjoint is the cellularization of that functor Singh C2 from before. This is a smashing localization. In particular, the right adjoint is fully faithful. And let me note, this also works at an odd prime, but the odd primary statement is far less interesting because the C2 take construction tends to vanish on P-complete objects. So from this statement, I can decategorify and obtain effective calculational methods that generalize the strategy I described for you for computing HF2. So that's why this work is relevant to electronic computational homotopy theory seminar. Let me now go into a sketch of the proof. So why is this being a smashing localization? To begin with, let's suppose I have a monoidal adjunction between 2 stable symmetric monoidal infinity categories C and D. By monoidal, I mean L is strong monoidal. If I have the following conditions, so R preserves colimits, R is conservative, and L and R satisfy the projection formula, then the so-called monoidal Barbeck theorem implies D is equivalent to, sorry, that's the wrong way. C is equivalent to modules. Excuse me, I had it right the first time. D is equivalent to modules taken in C with respect to the algebra object R of the unit of D. I learned this statement of the monoidal Barbeck theorem from a paper of Matthew Naumann and Noel, which is the first paper in their series. So this holds very generally for the adjunction of interest, namely C2 Betti realization and its right adjoint, Sing C2. And this is unconditionally, so without cellularity hypotheses and without completeness hypotheses. And likewise, for the cellular guy. Therefore, the interesting part of our theorem is the assertion that Sing C2, I should say cell Sing C2, is fully faithful. If I'm in this under the hypotheses of the monoidal Barbeck theorem, and I also know that the right adjoint is fully faithful, then I have a symmetric localization. So let's tackle the full faithfulness claim. Thanks to the so-called recollement, or recollement, I should say, on C2 spectra, which is given by taking the full subcategories of Borel C2 spectra and spectra, where spectra sits inside C2 spectra as the right adjoint, I lower star to C2 geometric fixed points. And I've already discussed the J upper star, J lower star junction. Well, the general theory of recollement, whatever those are, means that you can deal with the geometric and Borel parts independently, just like we did in the special case of HF2. So let's do that. The geometric part, let's take that adjunction. And again, I haven't imposed cellularity hypotheses yet between C2 Betti realization and Sing C2. Let's tack on the other adjunction, which is right adjoint is fully faithful. And let's see where suspension spectrum of scheme is sent. So again, I take the C2 space. If I take the geometric C2 fixed points on suspension spectrum, that's taking the C2 fixed points of the space and then suspending it. In this case, I get the R points of X. In other words, I learned that this composite functor is real Betti realization. Now, Bachmann showed the right adjoint to real Betti realization is fully faithful. Moreover, the localization endofunctor is computed by inverting that element rho in SHR. That's going to imply the claim from before that at the level of homotopy groups, I can compute, well, I can compute as follows. So that's it for the geometric part. As you can see, there's nothing new here. We're just using as an input Bachman's results. As for the Borel part, let me return to that picture from before. So I have SHR, SHC, base change, then C2 spectra, restriction, spectra, and that's realization. Now, adjoint to base change, I also have the push forward functor, and likewise the induction functor. And again, via using that monoidal Barbecke theorem, I get that SHC is equivalent to modules taken in SHR over spec C plus viewed as a real motivic spectrum. And likewise, spectra is modules taken in C2 spectra over C2 plus, where C2 plus, again, is the cofiber of the Euler class A. Now, let me warn you that spec C plus is not cellular. I want to lift the result at the level of BEC to BEC2, so I better impose cellularity hypothesis somewhere. Rather, the observation to make is that there exists non-canonical cellular two complete equivalents from the cofiber of rho to spec C plus. Quick reason as to why you know this is that if you compute HF2 star star both sides, you'll get that this is F2 adjoint tau. This essentially or implicitly uses that rho is null homotopic if I have a square root of -1, for instance, in SHC. And then you deduce the two complete statement using motivic atom spectral sequence. So that's very important for us. It matches nicely with the statement involving the cofiber of A in terms of C2 equivariant homotopy theory. So as a corollary, SH cell C is equivalent to modules over SH cell R, modules over the cofiber of rho taken in SH cell R. And I've implicitly two completed. This result has been independently observed by Isaacson, Kong, Xu, and Wang. Let's plug it into our picture where now I want to involve the A-complete and rho-complete categories. So this yields the following picture. SH cell R, C2 spectra, SH cell R rho-complete, SPHC2, which is SPC2 A-complete, and modules over the cofiber of rho, modules over the cofiber of A. The junction lifts, that's formal, and here, this is fully faithful by the result of Duggan-Isaacson from before. Formally, I deduce that this adjunction is fully faithful, and then combining the results on the Borel and geometric parts, you deduce full faithfulness, as in the statement of the main theorem. So that actually completes the sketch of the proof of the main theorem. So that, you can think of that as proving the main theorem in its categorical form. Now, there's one important question that remains. So it remains to show or to identify, I should say, I need to identify the localization functor on the homotopy completion. That's to say, this one over here, as inverting tau on the row completion. And the statement is not quite accurate, and I'll explain why. Well, the idea is that I have already a smashing localization. If I look at modules over the cofiber of rho to the n, and take that adjunction with modules over the cofiber of a to the n, these intermediate statements, they're going to imply some statement at infinity, because if I take the row complete category, that's the limit, inverse limit over modules cofiber rho to the n, and likewise for the other side. And I also formally have deduced that these adjunctions are smashing localizations by knowing it at the sort of base level, modules of the cofiber of rho and cofiber of A. So let's call that localization endofunctor Ln. And I can find some element tau sub n from desuspension 0 minus n cofiber of rho to the n to cofiber of rho to the n, which is a tau self-map. In the sense that Hurewicz homomorphism applied to this yields power of tau, such that the localization endofunctor Ln applied to x, it's computed by inverting that element tau sub n. Because I have the element tau sub n on the cofiber rho to the n. So I have it on any module. And you can do this. You can find this element tau sub n by lifting a un self-map on the cofiber of a to the n. This is a so-called un self-map because for n equals 1, the map in question is map u from the desuspension of 0 minus 1 cofiber of a to cofiber of a, which reflects the fact that non-equivariantly, I have an equivalence between S1 minus sigma and S0. And this story is slightly involved. I refer you to our paper to understand it completely. But let me just note, to end this talk, that the periodicity of these elements tau sub n increases to infinity as little n increases. However, you can still define the tau inversion of the row completion as the inverse limit over n of x mod rho to the n tau inverted. Let me warn you that in the paper, we don't try to understand the compatibilities of the maps tau n as n varies. Rather, we use the fact that I already have these smashing localizations for modules over cofiber of rho to the n for all n. So I know after I invert the elements tau n that I have compatibility. In particular, I can form this inverse limit. So with this definition here in the box, the earlier assertions for homotopy groups hold. And now let me show you some pictures to end this talk. So I did HF2. So you can also do, for instance, HZ2 the same way, organize this calculation in the same way. So the homotopy completion, you invert this element tau. For the geometrical localization, again, I invert rho. I combine these two operations, get the lower right-hand corner. And I use the Meyer-Vittori sequence again, and that you discover the C2 equivariant homotopy groups of HZ2 this way. That's a graphic which is present in our paper. We can also do connective KO theory. So by this, I should say connective part of Atiyah's real K theory, excuse me. So this is the C2 Betty realization of the effective cover of KGL. And you can see the calculation looks more complicated, but really the complexity, if you understand the motivity calculation, which is the point of this method, you can easily deduce the C2 equivariant calculation. And with that, I think I'll end it there. Open floor to questions.
First of all, I'm going to unmute everyone so we can thank him. Let's give him a round of applause. So thanks very much. Okay, now I'm going to go ahead and remute people to cut down on the background noise. Okay, and we'll open it up to questions then. All right, well, I have a question. To what extent is this method will be effective for computing the equivariant stable homotopy groups of the sphere spectrum?
So we actually use your results that they agree in a range in order to construct these tau self-maps. I suspect it's not so useful, but I haven't thought too much about that.
Okay. Other questions?
But I mean, so certainly works for any guy. It certainly still works for the sphere spectrum. So.
Right. Right. In theory, it works, but I meant like like practicality. Like, is it going to be too technical?
Yeah. So I haven't thought about that. Yeah.
Okay. Other questions? Okay. If not, then we will wrap it up here for today.